Let's talk about those current climate changes. First, I'll point out that it has little relationship to the ozone hole. People often conflate those. There are some small relationships between them, but it's really climate change is not related to the ozone hole very much. Current changes. Earth is warming, as we saw, about 1 Celsius over the past 150 or so years. The greenhouse gases in the atmosphere are increasing, and those increases are due to humans. Humans are what are releasing those gases. It's not volcanoes or dead things or carbonate sediments. And other forcings, changes in volcanoes, changes in the sun that we have measured, are not causing warming. If we consider what just those forcings are doing, temperatures should be neutral to slightly decreasing. So it's not the sun that's changing recently. And the effects of warming are evident now. We're starting to see changes in Earth's climate that aren't just temperature, that are related to those current climate changes. So it's having other effects too. Let's talk about the ozone first, just to get that out of the way. Ozone depletion is not a major cause of climate change. They tend to be separate problems. The ozone hole was first identified over, I think, the 60s and 70s, and global agreement in the 80s called the Montreal Protocol is something that we used to stop emitting some of the gases called CFCs, chlorofluorocarbons, that were destroying the ozone hole. The ozone hole being a problem because that lets in ultraviolet radiation, which can cause skin cancer and other cancers. So we wanted to put the kibosh on that as soon as we could. But it wasn't nearly as big a problem and as pervasive a problem as climate change, because these CFCs weren't super common chemicals. I will point out that there are some connections. Both ozone and CFCs are minor greenhouse gases. And ozone chemistry can affect how heat is distributed in the stratosphere. But really, for the most part, it's a very separate thing from what we're going to talk about, which is anthropogenic climate change. I also want to point out that this is one place to look for an example of how we as humans came together and solved an environmental problem. The ozone hole is repairing itself now that we have stopped outputting as many of those chlorofluorocarbons. And the hope is that we can do something similar to fix climate change before it gets too drastic. So I'm going to show you this video briefly just to demonstrate that Earth is indeed warming. This shows you a map of temperature over time. You'll see the year up in the corner. So we can see that the temperature record is somewhat sparse going back into the 1850s, 1800s. But we start to get better coverage as we come out of the 1800s into the 1900s. There hasn't been too much change so far. We've been mostly in the light blues to dark blues. As we come out of the 1920s, we start to see a lot more yellows, reds, and oranges. You can also see that averages really started to tick up. Since the 1980s, we've seen a whole lot of warming. Right now, the dominant color on this map is yellow to red to orange. And over the past few years, we've seen some pretty substantial warming. These are some of the warmest years on record. You can see that graph on the bottom showing just how much we've warmed on average since 1850. Here's another way of looking at some of that same data, where the yearly departure from the original average temperature, maybe, so the baseline here, they say, is 1850 to 1900. So using that as your 0 point, this is showing how seasonal temperatures have changed, color-coded by the year during which they occurred. And so the original purples and blues are earlier years, and the yellows and oranges are in later years. And we see those yellows and oranges reaching further and further out towards the 1.5 Celsius total warming line. We're getting very close. And many people have cited this 2 Celsius warming line as a line we really don't want to cross. But we're on our way there, and we're probably going to cross it. As I mentioned in a previous lecture, Earth is warming faster than any change in the past 20,000 years. We're relatively certain of that. The size of the change, the magnitude of the change, is smaller than what came out over the whole past 20,000 years since we came out of an ice age, where this is our current change. But the rate, the slope of change is nearly vertical. The rapid nature of this change far exceeds the rate of climate change over the past 20,000 years. So when folks say, it's been a lot colder in the past or it's been a lot warmer in the past, they're right, but they're really missing the point here, which is that we're changing climate so fast that it's possible that parts of the Earth system won't have time to adapt in a way that is good for humans. So why is it warming? Is it something natural? Well, we have measured greenhouse gases, and we know that those greenhouse gases have dramatically increased since industrialization, right? So since about the 1800s. Is that our fault, or is something else releasing that carbon dioxide? That's a reasonable thing to think. Just because carbon dioxide is increasing doesn't mean that it's human. And there are isotope signals from these different possible sources of the CO2. It could be from volcanoes, in which case it would have high 13C and none of that 14C that actually is generated in the atmosphere. CO2 from living things would have low 13C, but some 14C. And CO2 from fossil fuels, so stuff that's been dead a long time, would have low 13C and no 14C. So it gives us a signature to look for in this carbon dioxide. And when we look at the CO2 that has been introduced into the atmosphere and mixed with the rest of it, we find that it has low 13C and no 14C. So the isotope record is really what ties us back to the fact that that carbon dioxide increase is due to fossil fuel burning. It's not all fossil fuel burning, although that is a big part of it. So these parts here, coal, oil, and gas, are a big chunk of that burning. But there are other industries that have an impact too. The other major industry that has an impact is actually cement manufacture, where we take calcium carbonate, right, limestone and stuff like it, and we turn it into calcium oxide that we use in cement and produce carbon dioxide gas, which we just let into the atmosphere. So a big part of that CO2 increase is from the cement industry, although most of it is still from coal, oil, and gas burning. There are also changes to land use, deforestation and such, which causes breakdown of organic matter in the soil and also releases CO2. That would be about 10 to 20% of this. So you could add another little bit on top of that for land use. The top greenhouse gas emitters, so these are rates of emission per year, not total emission over all time, but the rate at which we're emitting greenhouse gases here. So China has certainly taken the lead at this point. They're emitting the most on a year-by-year basis, over twice as much as the US is emitting, although the US is still emitting a very large amount, followed by India with a similarly large population to China, and then followed by other industrialized countries, Russia, Japan, Brazil, and on down the list. The US is still the second largest emitter, and we are also the emitter that has released the most over time. So looking back over the past hundreds of years, we've still released the most, although China is certainly on pace to overtake us in the not too distant future. What does that mean for who should fix it? That's not something that we're going to talk about in here, but it's important to bring up. We can talk about the carbon footprint of various activities, various things that we consume based on how much carbon dioxide and also methane, which is even stronger than carbon dioxide in terms of global warming potential, how much those emit. So on this graph, we've got kilograms of greenhouse gas emissions per serving of the good stuff, right? So we look at things like beef, your average beef is going to emit a lot of greenhouse gases, 5 kilos per serving, right? And your servings are probably smaller than a kilogram of meat, unfortunately. You're thinking like 4, 6, 8 ounces maybe. Other meats, lamb, prawns, some fish, pork, have lower impacts, and some of them have especially low impacts, right? Depending on how you actually go about getting these, it can dramatically change the amount of greenhouse gases emitted, right? So your worst factory farms are emitting 15 kilos from each serving of beef, whereas something that's farmed as sustainably as they can, it's going to be more expensive certainly, but it's going to emit only maybe 2 or 3 kilos of greenhouse gases per serving. The meat, why is it that meat emits so much greenhouse gas? Some of it is the cow farts. That's true. Cows fart methane. But most of that is actually due to the fossil fuels burned to fertilize and harvest your feedstocks, your soybeans and such, your corn that you're going to feed these animals. Turns out that, to get a pound of meat, you need to feed them about 10 pounds of feed. And that 10 pounds of feed is going to take a lot of inputs from fossil fuels, going into fertilizing, going into, running your tractors on these lands. So there's a big impact that's outsized in terms of, meat over other things. I can't say that you should stop eating meat because meat is delicious, but it is something to think about. Let's look at our current climate record over the past 1,000 or so years. And in particular, this diagram is nice because not only does it show the temperature increase down here, but it shows what it is with humans and what we project it would have been without humans in a couple of these different reconstructions. Right? There's some error in between these different reconstructions because they always use slightly different numbers going in, but they're pretty tightly bound that with humans, it got a lot warmer than it would have been without humans. Well, how do we know that? Because we can look at the other forcings that are involved. These are the volcanic forcings up here showing changes in temperature, or really in the amount of solar radiation coming in, which we can translate into temperature due to volcanoes. So volcanoes tend to be negative forcings because they spit a lot of those aerosols into the atmosphere. They throw a lot of ash up there, and that tends to outweigh things like how many greenhouse gases they've emitted. We can also look at the forcings of solar irradiance, right? So the changes in Earth's radiation that it's receiving from the sun using our best proxy records. And we find that, over the past, certainly 50 or so years when the change has been the most severe, solar energy changes are not very substantial. So it doesn't seem like the sun is really responsible for this either. In contrast, you look at the impact of all other forcings, including greenhouse gases. And that's far and away what seems to be causing most of the increase. This is another set of those observations, which are the black line. And then we can sort of go back and we can reverse model using all the physics that we know to show what changes in things like surface temperatures of the land and ocean, or the ocean heat content, would have been without people, only using the natural forcings that we can measure, versus the changes that we would expect from natural and human caused forcings. And in each of these instances, our measurements, the black line, matches up with the natural and anthropogenic forcings and not with the just natural forcings, which we use to indicate that the changes that we see in Earth's climate are due to people, due to the forcings that people are causing, and not due to those natural forcings. So it's not only the temperature that's changing, but also changes to ocean temperatures, changes to sea ice extent. You can't explain those if you only use the natural forcings. This is a diagram showing the radiative forcing, that is, the changes to how much Earth's radiation budget is changing based on anthropogenic and natural changes. Right, so something like solar irradiance is increasing at Earth's surface very slightly, maybe 0.1 watts per meter squared, which is a way of measuring how much incoming radiation is going in. But these anthropogenic forcings are having much larger effects, limiting the amount of radiation that's going out. So carbon dioxide by itself is more than 1.5 watts per meter squared. So, right, the impact of carbon dioxide is maybe about 20 times what the impact of solar changes are. And that's carbon dioxide increases all from humans, as we already established. Other greenhouse gases are also pretty important. Methane, followed by nitrous oxide, and followed by other greenhouse gases as well. These are all also much larger than the changes coming just from the sun. There have been some other anthropogenic changes too, to ozone levels. It matters where in the atmosphere they are, whether they cause warming or cooling. And there are some uncertainties on all of these estimates. But those uncertainties are not large enough to change the headline conclusion, which is that our forcings, our changes to our radiation budget, dwarf natural changes in solar irradiation, even including the huge uncertainty on like what aerosols are doing. Like these uncertainties are really big, but it's not going to be enough to dwarf the fact, to prevent the fact that the total anthropogenic changes are much, much bigger than any natural changes going on today. If we break this down even further, we can see that CO2 is responsible for most of the change in radiative forcing that it's causing climate change. But you know, other things do still have that impact: CH4, halocarbons, nitrous oxide. Related things to those CFCs as well. And here's a concept that often gets referred to in thinking about climate change, which is equilibrium climate sensitivity. That is the change in temperature that we expect to happen from doubling the greenhouse gas effect, which really we take to be doubling CO2. Without any feedbacks, we expect that if you doubled CO2, that our temperature on Earth would increase only about 1.2 Celsius. We're getting close to doubling CO2 in the atmosphere from pre-industrial times. But we think that if we include the feedbacks that happen, most of them tend to be positive on, you know, decadal timescales, tens to hundreds of years. Positive is not good for us. Positive is actually bad for us, because as we increase warming, those positive feedbacks are going to cause even more warming. As a result, equilibrium climate sensitivity is somewhere in the range of 1.5 to 4.5 Celsius. That means that once we've doubled CO2, once temperature stabilizes, we expect it to be 1.5 to 4.5 degrees warmer than it was before we had an effect. 4.5 degrees Celsius might not sound like a lot, but as I'll show you, 4.5 degrees matters a whole lot at Earth's surface. If we're talking about the entire planet warming that much, that's huge. Warming is causing other effects other than just, you know, the temperature increase that's associated with it. Like we saw in lab, you probably saw that sea ice was decreasing in the Arctic. It's also causing land ice to melt in many locations, including on Greenland and in part of Western Antarctica. The total effect over all of Antarctica is sort of, you know, on average, this tends to be 0 when you add together the places that ice is growing versus shrinking. Whether that's always going to be true, it's hard to say. People are putting a lot of work into trying to figure that out. But in general, we do see a loss of ice up in the Arctic in the northern hemisphere, which is pretty significant. All that ice melting on Greenland, all the ice melting that is, you know, sea ice that's not contributing to sea level rise, because, you know, like an ice cube, it's already sitting in the water. So it's not going to change sea level as it melts. But that sea ice melting does mean that, right, it's going to impact feedbacks because we're lowering albedo now, and so on and so forth. So it's still important. Other effects of warming are evident right now. I'm just going to hit you with some of the greatest hits of what we see going on. So we mentioned sea ice extent dropping lower and lower, especially in the Arctic. Total record highs versus record lows. We're getting about 3 times as many record highs as we were record lows in the 2000s. So seems like, you know, the temperature records are being broken, but more often in favor of those daily highs instead of, daily lows. Flooding in flood-prone places like Miami Beach is increasing even in the absence of any storms. So these are just tidal flooding events have dramatically increased over the past 20 or so years. We're getting more and more flooding just during sunny weather, and that's because sea level is starting to tick upward. Big changes out west, the changes in the snowpack that really provides a lot of water to those western states, including a lot of ranches that are feeding those cattle that we're all eating. The snowpack in those places is really dramatically decreasing, which we have attributed to climate change. Other things that we can directly see, sea level has increased only by about 8 inches. And I say only 8 inches. That matters if you're right on the beach. And that sea level continues to increase as we continue to release greenhouse gases. There might be an effect on wildfires over the past 30 or 40 years. That's harder to tie directly to climate change because there are a lot of other policies that influence it. You'll have to look at some of the more current research to know whether that's directly related to climate change or whether that's just another impact that we're having on our environment. Heavy precipitation events seem to have increased over the past 50 years as well. Also harder to tie to climate change, but a lot of folks think that that's due to the effects of climate change. And then the jury's kind of out on the number of hurricanes. I don't look at this and see a very dramatic increase in the number of hurricanes total, right? Maybe there's a slight increase around the globe. Hurricanes reaching the United States has been relatively flat over the past 100+ years. So hurricanes, I'm not really sure. You'll have to ask other scientists about that, whether there's even, much of an impact there. But I do know that we continue to develop the beaches. And so if we have sea level rise impacting us, then each of those hurricanes is going to cause higher and higher storm surges.